So welcome everyone to the first advanced session on discrete event simulation. I'm going to start with a little bit of a recap on some of the key points that we mentioned in the first discrete event simulation session. And if you remember, we talked about what discrete event simulation was. You had a chance to think about how you might go about building a conceptual model for a discrete event simulation, so how you take a sort of real world messy problem and how you'd focus that down and how you might then translate that into the design for a discrete event model. And then at the very end, I showed you briefly a SimPy model, but I just sort of briefly talked you through it to give you an idea of the sort of thing that what a SimPy model looks like, basically. So I'm going to do that again today, but today you're going to be having some hands-on practice, actually building some SimPy models. I'm also going to go into some of the more detailed information about SimPy, some of the more detailed features that you can use. Now, it's important. One thing that's important to note about SimPy is that you can use it in both object-oriented and non-object-oriented form, and the structure is quite different. Now, the way I've decided to do this is to show you the non-object-oriented approach today. So we're not going to be talking about the object-oriented approach to SimPy today. The non-object-oriented approach is easier to get into. It's more accessible, and hence the reason I want to start with that. What you will find, though, is that if you build anything beyond a fairly simple model, it can start to get quite messy because you have to pass things around all over your code, basically. And that's fine, and I've built models like that. But that's where the benefits of the object-oriented approach come in. So in the second advanced session, part 2, which we'll do next week, I think, I will show you how to do the same thing but in an object-oriented structure. And that initially can look like it's using a sort of hammer to crack a walnut. It looks very over the top. But what you'll see is that once you get into the swing of using that structure, when you then scale things up and you're building more complex models, it makes it much, much easier in the long run. But as I wanted to separate those things out, because if you just want to focus on the non-object oriented approach, this is perfectly valid. This will work for all of the models that you want to build. It's just that if you build a more complex model, it'll start to get a bit sort of messier. That's all. So let's have a quick recap on discrete event simulation. So we talked about discrete event simulation as being a modeling method in which you're essentially modeling entities that are flowing through discrete sequential processes. So they're typically used to model queuing problems or problems where you've got a series of activities, and associated with each of those activities are some sort of resource, and that constrains the amount of time that resource can spend with the entity that's flowing into that activity. So because of that, they're very often used in healthcare, for example, to model patient pathways. We talked about the nomenclature of discrete event simulation. Let's just remind ourselves of the things that we're talking about. So our entities are the things that are flowing through those sequential processes in our model. Very often there'll be people, so patients, or might be victims, or if you're doing policing stuff, whatever it might be. But it doesn't have to be people. It could be things like telephone calls. You can model a call waiting system using discrete event simulation. That's commonly done. Or things like blood test results. Anything that's flowing through a series of processes and is queuing, waiting for resource for those processes, can be modeled as an entity. Then we've got generators. So generators are the things that create the entities. They bring them into being in the model. So that's how they the start point, if you like, of the entities. And you may have more than one generator. So you might have, where it's important, you might have multiple ways in which a patient can come into the model, for example. So in this example, you might have patients coming into the ED, and you might model separately the patients arriving by self-presenting versus patients who are being brought in by paramedics, if that's important. We've also got the concept of inter-arrival times. This is very important in discrete event simulations. Basically, it just represents the amount of time between entities being generated, i.e. arriving into the model. And normally we model inter-arrival times using a distribution. So we sample randomly. We have a mean, but then we sample randomly from that to account for the variability and the fact that, you know, not everybody turns up in exact 3-minute intervals or 4-minute intervals, unless you're modeling, of course, a strict appointment system, in which case you may want that structure. Then we've got activities or servers. These are the things that represent the activities that happen to entities. So things like triage, treatment, ward admission. These are the things, the stuff that's happening to our entities, the processes. And with each of those activities or servers, we have an activity or server time, which represents the amount of time it takes for that activity to happen. And as I say, as with inter-arrival times, we typically model activity or server times with distributions to account for variability, because, you know, not everybody's going to spend exactly the same amount of time usually in a process. So you know, if they're being registered at the registration desk, it may take on average 2 minutes, but there'll be variability around that. The other thing we need for activities is resources. Typically, we need resources in order for these activities to happen. And those resources might be shared between activities. So you might have nurses who are doing multiple different things. And so if somebody's queuing for a triage up here, they need to wait for a nurse to become available, but the nurse may be also doing other things as well. Queues are essentially where our entities wait until the activity has the capacity and the required resource to begin. Often they are physical queues, but they may not be. So you may have an actual physical queue in which people are standing and waiting. You might have a kind of waiting room style queue where people are sort of sitting and waiting, and they may be prioritized in some way. And you may also have a more abstract kind of queue where they're on a waiting list for something, and it may take place over a longer period of time, for example. Still be a queue in this kind of model. And then the last thing we need is sinks. And sinks are basically how our entities leave the model. So they're the opposite of our generators. And that doesn't necessarily mean that they've left the system, the real world system we're modeling. It means they've left the bit of the system that we're modeling, and we no longer need to model them in our bit. So remember, back in the very first session, I talked about the idea of scope, and you have to work out how much of your real world system you're going to capture in the model, both in terms of the level of detail, but also in terms of the scope, i.e. where does it start and where does it end. So it might be, if you're just modeling the ED, that your sinks represent them leaving ED, either because they've been discharged or because they've been admitted or whatever it may be. But you may not then need to model anything beyond that. So the sinks are how they leave your bit of the model. Now, you remember the other thing that I talked about in the first discrete event simulation session was something called a generator function. Now, this is not to be confused with a discrete event simulation generator. So discrete event simulation generators are the way in which our entities come into being. There are entry points in our model. Generator functions are different. These are things in Python which are these kind of magical functions that work just like our normal kind of functions, but with one key difference. So if you remember, a normal function that we write in Python, we give it a name and we say what inputs it needs, and then we tell it what the function should do, and then we finish, and usually we return some output, although not always. But when we call a conventional function in Python, it runs, and then it finishes, and then that's it. And then when we call it again, it starts again, as though it's never been run before. But a generator function is different. It acts in exactly the same way, except that when control is passed back, i.e. when something's returned, they will freeze in place, so that when they're then called again, they will then carry on from where they left off. They won't go back to the start of the function. They will carry on from exactly the point they left off. They'll be sort of unfrozen in time. And because of that, they can be used as powerful iterators. So let's just have a look. I think Oh no, I don't think I've got that one in here. Is that one? No, that's not the one. Let me show you on here instead. So, if you remember, I showed you this example last time, and I showed you the difference between a normal function and a generator function. So the normal function, we might have a function where called keep count, and sorry, that's not the that's the conventional function here. So we might have a normal function called conventional keep count here, start a count at 0, and we have a infinite while loop that just says increment 1 to the count and then return it. Now, if we were to run that, every time we run that function, it'll set count to 0, and then it'll go into this while loop here, and it'll say, okay, increment count, so count is now 1, and then return it. Then we print out the result, the thing that's been returned, and it would print the number 1. But then when we run that function again, it'll just go back to the start. It'll say, okay, count's now 0, so I'll go back through. So every time we run that, it'll give us the result of 1. But a generator function would work differently. So in here, we've got the same structure. We've got a count set to 0 at the start. We've got an infinite while loop, and in that infinite while loop, we basically increment the count by 1 and then return that value. Except we use this word, the yield keyword. And that's basically a replacement for return, which tells Python, this isn't a standard function, this is a generator function. So yes, I want you to return count, but I also want you to remember exactly where you are so that when I call you again, you can unfreeze and carry on from where you left off. So if we were to run this function, the first time we run it, it'll set count to 0, and then it'll enter the while loop, and it'll add 1 to the count. So the count will now be 1. It'll return that. If we print that, it'll come out with a value of 1. But then when we call it again, it'll pick up from here. It'll say, okay, well, that's where I was. So the next thing I'm going to do is go back around the while loop. So now I'm going to increment 1, another 1 to the count. So now count is 2. And then I'm going to return that and freeze in place. So now count is 2. Then when it comes back, okay, I'll unfreeze again. Now I'll carry on where I left off. And the reason we're telling you so much about it, I mean, these are useful functions, types of functions themselves, but they are the fundamental principle around which SimPy is built. So essentially, that's the key difference with the generator function, that it's just like a normal function, except when you return something, it freezes in place so that when you call it again, it will carry on from where it left off. It won't go back and run it as though it's never been run before. So let's remind ourselves of the example SimPy model that I showed you at the very end of the last session, which uses these generator functions. So this is just a really simple model that models this. We've got people arriving for a weight loss consultation. They're then queuing for that consultation, which needs a nurse, and then they leave. So really simple model. And that requires just a really simple discrete event simulation. But it is a discrete event simulation because we've got an activity, we've got entities, the people arriving, we've got a generator which generates those entities, we've got a queue forming as they wait for this activity, and then this activity needs a nurse for it to happen, and then they flow out to a sink. So here our inter-arrival times are the times between arrivals of people wanting a weight loss consultation, our entities are patients, and the activity time is the time they spend in that weight loss consultation. So let's show you, I have got this one up. I'll show you here. So this is how we build that very simple model in SimPy. So the first thing we need to do is to import SimPy. That'll bring in the package and all the magic stuff that's going to be used. And I'm also going to import random because we're going to need to randomly sample from some distributions. So the random library is going to be your best friend when it comes to discrete event simulation because it'll allow you to model these distributions. Now we've got basically 2 generator functions to model this. And here's where I emphasize again the difference between a generator function and a generator in discrete event simulation. So remember, generator in discrete event simulation is the thing that brings our entities into being, whereas in Python, a generator function is these kind of magical functions that freeze when you return something and then carry on where they left off when you call them again. So essentially, how we represent this in SimPy is to have this simple model is to have two generator functions. We have one generator function that basically emulates our discrete event generator, i.e. this is generator function will bring our entities into being, and it will keep generating new patients. And then the second generator function will basically describe the journey that that patient will take through our system. So all of the activities they're queuing for, the resources they need for each activity, etc., etc. So you've got a generator function that represents a discrete event simulation generator, i.e. it's creating new patients. And then we've got a generator function that describes the series of things that will happen at the journey of that patient through the system. So let's look first at the generator function that emulates a discrete event simulation generator, the thing that's going to create our patients. So because this is a function, it's a generator function, but the only difference is this yield keyword. So we define it in the same sort of way. So we use the def keyword to define our function, and then we give it a name. So I've called mine patient generator weight loss. Now I could have just called it patient generator, but it might be that as we build on this model, it might be that we have different types of patient coming in and we want to model the different entry points. So I might want to have a patient generator for people coming in for the stop smoking clinic, for example, and I may want to model that differently. So to future-proof it, I've specified this is a patient generator and it's for the people coming in for the weight loss stuff. Now the inputs that we need to pass in are everything this generator is going to need. And the thing that it'll always need is this, which is the SimPy environment, which I'll show you how to set up down below. But we need to pass it the environment in which this model is going to run. And that's the thing that does SimPy does all the magic in, basically, and allows us not to have to worry about much of this stuff. I'm also going to need to tell it, I'm going to pass in the inter-arrival times, because this generator is going to need to know how often it should be generating new patients. So we'll need to pass in the inter-arrival time. I've just called mine WL for weight loss inter-arrival time. And I'm also going to need to pass it two things that it will need to pass on. And that is the average consultation time and the nurse resource. Now it's going to pass those things on because all this function is going to do is basically create a new patient and then start off the other generator function, which tells them, and this is your journey through our system. And it will start them on their merry way and say, here you go, here's the time you're going to spend with a nurse on average. Here's the nurse, here's the model, here's your patient ID, go forth. That's basically what this generator function does. It creates a patient and then sends them on their merry way. So in order to do that, we need to pass in here the things that we'll need to be sent on its merry way with. And those are the mean consultation time, in this case, the mean consultation time and the nurse resource. So what I'm going to do in this generator function is, the first thing I'm going to do is set up a patient ID. Now, obviously, if you're doing this for real, you may have different ways in which you generate the ID, but in this case, I'm just going to have a simple ID that basically just increments. So every patient that's generated has an incremented number. So the first one will have a patient ID of 0, then the next one, patient ID of 1, 2, 3, etc. And that may be all you need for a lot of what you do. It's just a way to identify your individual patients in your model. So I've given it, started off the patient ID at 0. And then I'm going to put everything else in an infinite while loop. And what this basically says is just keep doing this while this program is running. Just keep doing this. And remember, while true gives us a handy shortcut for an infinite loop, because true is always true. So we can say while true. So keep doing this until this program stops. And the first thing I'm going to do is create an instance of the activity generator. So basically, I want to set. Well, it's not strictly speaking an instance, but I want to set the activity generator running. So this is the other generator function that's going to describe the patient's journey. So what I want it to do is to basically start sending them on their merry way. So I'm going to call this function, and I'm going to assign it to WP, and I'm going to pass in the things the journey function is going to need. And that is the environment, because you have to keep passing that thing around to everything it needs. The mean consultation time, the nurse, those are the things it's going to need. And I can give it the patient ID as well, because I've generated it here. What I don't need to pass across is the inter-arrival time, because only this generator, the patient generator, which is creating the new patients, needs to know the inter-arrival time, because that's just the time between new patients coming into being. So I don't need to pass that on, but I do need to pass on the rest of it, and I'm also going to pass on this patient ID. Then I'm going to tell SimPy to run this activity generator for this patient. So I'm passing in the variable I created here, WP, and I'm passing in that into the process method of the environment. And that will basically say, now start this activity generator running. Okay, so here we said that's the generator function. So in some ways, this is essentially creating an instance of that activity generator. And then here you're saying, now start it running. Okay. Once it's done that, so essentially it's created the patient's journey, and then it's sent to that patient on their merry way. So all it now needs to do is to say, right, how long until I create the next patient? And so what it's going to do here, I've just got it drawing from an exponential distribution. So remember, random.expovariate gives us a sample of an exponential distribution. And remember, we passed in the mean inter-arrival time here, which I called WL inter. And remember, when you sample from an exponential distribution in Python, we need to specify lambda, which is 1 over the mean. So if I've got the mean, then I need to pass in 1 over that mean. So that's what I've done here. So that basically says, right, work out how long it's going to be until the next patient comes in, randomly sample from the distribution. And once it's done that, it can say, right, I know what time the next patient's going to come in. I know how long I've got to wait. So now I'm going to use the yield keyword, which makes this whole thing a generator function. And I'm going to pass control back to the SimPy environment. And I'm going to use this timeout function, which basically says, I'm going to wait here until it's time. You tell me that the simulation time has now passed, where I'm ready to create a new patient. So freeze in place. So if I sample 10 units of time, then here control will be passed back to the SimPy environment. And when we get to the 10 units of time have passed in the simulation, it will then pass control back to this generator function. And because it's a generator function, it will then carry on from this point. It'll start where it left off. It won't go back to the start. It'll start from here. So the first thing it will do then, when it's time for another patient, is to start here, and then it'll go to here, and it'll say, okay, so I'll increment my patient ID by 1. So the second time this comes through, the patient ID will now be 1, and it'll go back around the while loop, and then it'll create the instance of the activity generator here. It'll start that running, and then work out when the next patient's coming in. So it's basically just keeps going through this loop of saying, here's your journey, go on your merry way. What time's my next patient coming in? I'll wait until that time has passed. And you'll just keep doing those things each and every time. Send them, create the activity generator, which describes their journey, tell it to start off, and then work out when your next patient's coming in, and then freeze in place. And those 4 things you'll basically do pretty much every time you set up a generator function for a discrete event simulation generator in SimPy. Those are the 4 key things. You may do some other stuff as well, but those are the 4 key things that you will do each and every time. So that's the patient generator. That's the thing that's generating new patients. But let's now have a look at the activity generator. So this is the activity generator function that is basically describing the patient's journey. So that's the thing that we're starting off running up here for each individual patient. So for the activity generator, remember we passed it across the environment. We needed to give it the mean consultation time with the nurse itself as a resource, and the patient ID. So those are the things we need. The first thing I can do in this function, so when this is called, this will be when a new patient's been created, and it'll then start running. So the first thing we can do is to record the time at which this patient entered the queue for the nurse. So in this case, it's entering the system, but we've only got one thing in our system, and that's queuing for a nurse. So we can record this, the time they came in, as, okay, they started queuing for a nurse now. And this now method of the SimPy environment basically just grabs us out the current simulation time. So the simulation time will start at 0, and then it'll increment in time units. You can use those time units to represent whatever you like, although you need to make sure you're consistent. Typically, when you're doing discrete event simulations, you often use minutes, your time units to represent minutes, because usually you would describe your processes in terms of minutes. But obviously there may be situations where you go much higher level or much lower level. So we can record the time that the simulation time now, when this thing starts. So now they've started queuing for the nurse. And here I've just printed a simple message saying, this patient with patient ID, whatever it is, has entered the queue at that time. So now what I need to do is request a nurse. We've got the patient waiting, so we need to request a nurse. You remember I said we can use the with statement to do this. So you're familiar with seeing the with statement when you're opening a file. It says, basically, keep this file open whilst you do all this, and then automatically close it. Here, we're saying, with a nurse, do all of this stuff with a nurse, and then as soon as you've finished with it, release it. So here, we're saying with request for a nurse. So the nurse is a SimPy resource. That's an instance of the nurse, the resource class in SimPy. And I'll show you down below in a minute how we set that up. But nurse is basically an object that is an instance of the resource class. So we're saying with this nurse resource, I want you to request one. So with that request, do all of this stuff. And the first thing it needs to do is to basically wait until the request can be met, because it might not be that there's a nurse available at home. The nurse might be busy. So we use this yield statement as the generator function's alternative to a return to say, wait until the nurse is available. I will wait here. I will freeze in place until you can give me and meet that request. So it'll pass back control to SimPy, and SimPy will then note that somebody is waiting for a nurse, and then as soon as one becomes available, then control will be passed back here. And so because of that, it means when control is passed back, this being a generator function, it will carry on from this point. And so then the first thing we can do is say, okay, well, the nurse is now available, so I can now look at what time it is now, and that'll allow me to calculate how long the patient was waiting. So again, I can use my env.now to say what's the simulation time now, and I'll store that as the time left the queue for the nurse. And I can print a little message if I like, saying they left the queue at that time. And then I can just calculate how long they were waiting really simply, just by saying, well, it was the time they left the queue minus the time they joined the queue. So it might be if they're the first patient in and the nurse is ready and waiting, that time is 0, that they enter the queue here, and then we enter this here. We freeze the function in place until the request can be met, but it can be met immediately, and so the controls pass straight back. No simulation time has elapsed, and so we queue for 0 time units. But you'll often find in your models that certainly as time goes on, you'll start to have queues forming that they need to wait for this nurse, for example, to be available. So that's just me calculating how long they spent in the queue and then printing that message. The only thing I need to do now, so now the nurse is available, patient's ready and waiting. So we need to emulate this process. So in this case, we're emulating the patient coming in for a consultation about weight loss. So we need to generate in discrete event simulation terms, all we need to represent that process is the resource that's needed, in this case, the nurse, and the amount of time that the entity will spend with that resource. In this case, how long will the patient spend in the consultation? So again, I'm going to sample that from an exponential distribution using random.expo variate. Again, I pass in the lambda value, and I've got the mean here. I passed in the mean as being the average consultation time. So it might be the average consultation time is 5 minutes. It'll sample from an exponential distribution that has a mean of 5 minutes. That will be the amount of time that this patient will then spend with the nurse. And once it's got that, just as with the other generator function, it'll then say, okay, now freeze in place. Now, of course, the difference here is that they are freezing in place within this with statement, which means the nurse is frozen in time with them. So if we've sampled 10 minutes from this sample here, this function will then freeze in place for 10 minutes, for 10 time units of 10 units of simulation time, I should say, sorry. And as it's frozen, that nurse is frozen with it. So that nurse now can't be used by somebody else whilst that time is elapsing. And so that's how we capture this idea that the nurse is busy with a patient, because they're being frozen in time along with this patient. And so here, using the yield keyword, it basically says freeze for that amount of time you said it would take, and freeze the nurse with it. Obviously, if we've done this outside of the with statement, that would not work. That would not freeze the nurse with it. But because we've said, do all of this, you can only do this with a nurse, the nurse is required for all of this. Now, the only thing that takes simulation time is this, the timeout, where it's then saying, pass control back, and then tell me when 10 time units have elapsed, and then I'll carry on from where I left off. And of course, when that happens, because it's a generator function, it'll resume from this point, and the next thing it'll do is now, okay, well, I've exited the with statement now, so the function has dropped and ended. And so now the nurse is now free again because the with statement has ended. So those are the two key functions that we've got. We've got two generator functions. One of them is representing our discrete events generator, which is bringing into being, creating our patients and sending them on their merry way, and then working out the time to the next one, and then freezing in place until that elapses. And then the second one is describing the journey that each patient that's generated in the first function will make. And in this case, it's just to have a single process with a single resource. And so we record the time they come in. We then say we need this type of resource. It freezes in place until that can be met. And then we record how long they were waiting. And we sample how long they spent with that resource. And then we freeze in place until, with the resource, until that time has elapsed. And that creates our model. Those two functions create our model. So the only thing we have to do down here is to basically set these things running and pass it the information it needs. So here I've set up our simulation environment. So you'll always set up your environment like this, which is you just, and it's convention just to call it env. You can call it whatever you like, but env is the standard. And we say that's a SimPy environment. So we've created an instance of the SimPy environment class. This is the magic environment that's going to control all this for us. This is doing all the hard work, so we don't have to tell it what an entity is or what a generator is. We don't have to do any of that. It understands all these things because that's the beauty of using SimPy. So that's going to do all our control for us, and that's going to be the environment in which our model lives. So then all I need to do is set up my resources. So I've only got one resource in this model. I'm going to call that nurse. And that's an instance of the resource class of SimPy. And I just need to pass it two things: the environment in which it's going to live, which I've set up here, and the capacity, i.e. how many of this type of resource I want. So if I've got one nurse, then my capacity is 1.
Sorry, can I just ask something?
Yeah.
Instead of having the capacity one person, could you have that as resource hours?
Yes, you can, and I'll come on to that later. You do it,
Okay, great.
you do it slightly differently. You use something called a container, but I'll show you that
Okay,
later.
thank you.
So yeah, so in this case we've just got one nurse. If I wanted to, and that basically allows us to really easily check a question. So if our question was to model this and say, what's the benefit of having a second nurse, we can just do that. And that's as simple as that. So it really allows us to very easily test out different types of resourcing, which is one of the most common questions that you'll have in discrete event simulation. What if we remove this resource? What if we added extra resource in this part of the pathway? So I need to set up my other parameter values as well, which is in this case is the inter-arrival time. So here I've got patients arriving every 5 time units. I'm going to use minutes. Essentially, they're representing minutes for my model, and a mean consultation time of 6 minutes. And so as we mentioned before, we would expect, just from looking at that, there's probably going to be a queue building then, because if on average people are coming in every 5 minutes, but on average it's taking them 6 minutes in the consultation, then we're going to expect a queue to be forming because people are taking slightly longer to be seen so the nurse can't get through them quite as quickly as they are coming in on average. So we'd expect to see gradually a little bit of a queue forming. All we then need to do once we've got all that set up is to start up the arrivals generator, which is the thing that's going to start creating our patients. So we use the process keyword, process method of the environment, and we tell it to start this generator function, which is specified. We've called the patient generator weight loss. And we pass it those things we've set up here. And then we just tell it, right, run the simulation, go forth. And you can use this until keyword as an input to the run function to say how long to run for. So here I'm going to run for 120 time units. So that'll be 2 hours if these represent minutes in our model. So run this thing for 2 hours. So all I've done outside of these functions is to set up the environment, set up whichever resources I want. Here I've just got a single resource of a nurse, and I've just got one of them. Set up my other parameter values, so inter-arrival times, process times, etc. Then start up the generator function, the arrivals generator. Now, of course, if you have more than one arrivals generator, because you may have, as I said at the start, you might have different ways in which a patient can enter the system. So you could start them all up here. And then once they're all started up, just run the simulation, tell it how long to run for. So let's run that, see what happens. Okay, it's finished. Apologies, you probably won't be able to see this very well, but if you look here, so we've got the first patient coming in, patient 0 entered queue at time 0. They then left the queue at time 0 because of the first patient in. The nurse isn't busy, they're waiting. So they queued for 0 minutes. Then patient 1 entered the queue at time 6.79. Remember, we are randomly sampling from a continuous distribution, hence why we've got these time units. You can, if you so wish, have only discrete time units. You can convert it, but we usually don't need to do that. But look what happens here. So we've got patient 1, so the second patient, arrives at time 6.79. But then patient 2 enters about half a minute after them at time 7.2. So we can see patient 2 is going to be waiting. And then sure enough, patient 3 then comes along about half a minute later. And then patient 4 comes along. We've started to got a bit of a queue building already. And see, patient 0, that very first patient that came in, actually in this case, spent quite a long time with the nurse. They spent 15 minutes with the nurse. So in that time, we've had another 5 patients who've all come in and they're all waiting. So we've immediately got a queue that's built up, which means only now can patient 1, the second patient that came in, who came in at time 6.79, they were queuing for 8.64 minutes waiting to see the nurse. But then, of course, patient 6 comes in, so now we've got a building queue and a building queue, etc. And you can see as you scroll down through, in this case, there's quite a queue building, such that the last patient that came in, I remember this is only over 2 hours, had to queue for over an hour to see the nurse. So clearly, sorry, that's not even the last patient, that's the last patient that was seen in those 2 hours. So that's what we would describe a pretty run of bad luck there, because the first patient basically knocked things off because they spent a much longer time with the nurse. But of course, that may happen. That's exactly the sort of thing that can happen. And that's why we capture this kind of variability within a model, because not everybody's going to spend 6 minutes with the nurse and arrive every 5 minutes. You might get something like this happen, and then it could throw your entire system out. It might be that your system is really sensitive to the fact that if a patient spends a long time, you get a single patient that spends a long time with the nurse, everything else falls apart. Now, of course, that's only one run, and we wouldn't base our results just on that single run. And later, I'll show you how you would run a model lots and lots of times very quickly to say, okay, I'll try it with lots of different combinations so that you get a better idea of the average results over those runs. You want to get a sense of what the system looks like in general, not just what would happen in this particular random sampling. So that's basically a SimPy model. Let's now have a look. So that's just a very simple SimPy model. But in most discrete event simulation models, we'd have more than one activity in our system. So let's first consider a linear example where patients come in, they queue for one activity, and then when they're finished with that activity, they then queue for a second activity before they then leave. So this is starting to look a bit more like a real-world system where there are a couple of different things are happening to them. And obviously this applies to no matter how many processes will happen to them. So it could be they've got a queue of 10 things that they need to go through. So here, in this example, we've got patients arriving at the ED. They're then queuing to be registered by the receptionist. And then once they're registered by the receptionist, they then queue for a nurse who's going to triage them, and then they leave. So that's the model we want to build here. So let's look how we'd change the model to do that. So here we've got exactly the same structure we had before. We've got an arrivals generator function, and we've got an activity generator function. Arrivals generator works in exactly the same way as before. Obviously, I'm passing it slightly different things. So here I've got my ED into arrival time, and I need to pass it both a mean registration time and a mean triage time, and also two different resources, a receptionist and a nurse. But the principle is exactly the same. That we're creating creating a new instance of the activity generator, then starting that activity generator running, and then sampling how long until the next arrival, and then freezing in place until that happens. So those exact 4 things every time. Here, though, is where it will slightly differ. So here, instead of one process, we've got them having one process of a receptionist who's going to register them, but then after that, a second thing needs to happen to them. They need to be triaged by a nurse. Now, the great thing about SimPy is that is incredibly simple to do. So here I've got our activity generator function. The first thing that's going to happen is they're going to queue for registration. So I can record the time they entered that queue, just as we did before. So I'm going to request a receptionist resource here and do exactly as I did before, freeze in place until that request can be met, record the time that they then left that queue, then work out, randomly sample how long they're going to spend being registered, and then freeze in place along with the receptionist until that time has elapsed. So that's all as you've seen before. Now, all we need to now do is then model the next bit, which is the triage. So now we are outside of the with statement. So if I now have some follow-on code that comes outside of that with statement, that means the receptionist has now been dropped. They're now back in the pool, ready to be used by someone else. So now I can just simply repeat exactly in the same way that I did up here, but for the triage. So I just say, okay, right, they've now entered a queue for triage because they finished with the registration. So record the time now, and then have another with statement that says with the nurse as a request, then freeze in place until that request can be met, and then record the time you left, sample how long you're going to spend with the nurse in triage, and then time out. So you're just basically repeating exactly the same thing as above, except you must come out of that with statement. Now, probably one of the most common errors you will make when you start writing these things is to forget to do that. If you were to write and stay within your indented code within the with statement and then start on the next bit, And of course, what that means, essentially, you're saying, right, well, I need the receptionist to come with me when I get triaged by the nurse, because that receptionist will continue being held whilst it's in this with statement. So be very careful about that. However, you may have noted you might want to do that. There may be certain situations where, excuse me, where you might use a resource, or maybe a triage, but then that nurse may then come with you to the next part of the process. So you might actually want that to happen, where you've got you want the nurse to be frozen in place and to come along with you, as well as the doctor that you're seeing, for example. So you need to work out what's happening in your real world system, but normally you go through a process. That process has certain resources attached to it. You freeze those resources in place while that activity occurs, and then they're automatically released because you come out of the with statement, and then you start on the next bit. So that's all you need to do for a linear process like that, is to set up one thing and then come out of the with statement and then do the next bit in exactly the same way you did before. So it's really easy to do that. So that's an example of a linear process. But of course, in the real world, not everything is linear. In fact, there's a lot that isn't linear, because different things may well happen depending on certain conditions. So, for example, after the patient's been triaged by the nurse, they might be referred to the ambulatory care unit, so that they can diagnose and treat the patient without them being sort of admitted to the hospital. Or they might join the queue to see the ED doctor. So different things might happen depending on what happens in this triage. And it might be that we just model this. So in this example, let's just say that 20% of those who are triaged go and wait to see an ACU doctor. They go into the ACU, and the remaining 80% stay in the ED and wait to see an ED doctor. Now, we can model that really easily in SimPy. Can anybody think of how we might do that? The answer is simpler than you might imagine.
Do you put an else or in or something like that?
Yeah, basically.
You know.
Yeah, the if statement, exactly that. So we're basically just say, if this condition is true, then do this. Otherwise, do that. And that's all we need to do. And that's the beauty of using SimPy, a package that's built in Python, because we can just use Python syntax that we already know, conditional logic, to do this for us. So let's have a look how that would work. Where are we? Okay. So if I go into this model, so it's exactly the same as before up here. So I've got the receptionist, they queue for a receptionist, have the registration, and then they queue for a nurse, and then have the triage. Now, after that, we've added in these extra bits. And so all I've done here is to say, okay, well, if 20% of them are going over here and 80% of them are going over here, then what I'll do is I'll randomly sample from a uniform distribution between 0 and 1 to decide, and you've seen this done multiple times, where you basically pick a number between 0 and 1, and then use that to work out whether it's less than a certain threshold value. And if it is, you can say, well, that represents 20%. So here, if I sample a value that's between 0 and 0.2, then there's a 20% probability that I will do that. And therefore, that can emulate the chances of this patient going to the ACU rather than staying in the ED. So all I then need to do is use an if statement, say, well, if that's less than 0.2, then do all of this, which is exactly the same as before. So here it's going to be for the ACU assessment. So record the time entered, request the ACU doctor, freeze in place until they're available, work out what time they left the queue, how long they spend with the ACU doctor, and then freeze in place. But all of that will only be done if we've decided this patient's going to the ACU. But if we sample one of the 80% of values that isn't less than 0.2, then all this will happen. And so exactly the same, except this time it's with an ED doctor. So you can just use really simple conditional logic to branch off into different paths. And it might be that, for example, you don't need an else. It might be that the two options are that they stay for an assessment or they go home and leave the model. And in which case you just have an if statement to say, do this if that condition is true. But you don't need the else, because if you don't have the else, then they'll just drop off and they'll leave the model. So you can do both linear and non-linear pathways really easily using SimPy. The other thing you probably will want to do when you're building a SimPy model is to store some results over the simulation run, because we may, although we might be interested in seeing, okay, so patient 2 was waiting for 4 minutes, patient 3 was waiting for 7 minutes, etc. That doesn't mean too much individually because these are just random numbers that are being plucked out. What's more interesting is to look at the system as a whole and say, okay, so how long on average are patients queuing for the nurse? How long on average are they waiting to see a doctor? So one way we can do that is to set up a list that will store the results that we're interested in, and then we can add each patient's results to the list as the simulation goes. Now, if we're going to do it in that way, we need to make use of something called the global keyword, which you won't have seen so far in Python, but it's actually very simple. So let's have a look. So here, this is exactly the same model as we had in the initial model, the simple patients queuing to see a nurse for a weight loss consultation. So we've got our arrivals generator function here and our activity generator function here. Now, the only difference is I've added in some ways to capture the results. So here, if I go down to the bottom first, we've set up our environment and our resources and everything in exactly the same way. But I've also added this. I've set up a new list and I've called it list of queuing times for the nurse. So that's going to hold the queuing times for each patient. So then we can easily take an average over all of the queuing times once the model is finished. So because I've set it up down here, I need to refer to that within this function, the activity generator function, because that's where I'm going to add each queuing time. Now, strictly speaking, in Python, any variables that are outside of the function don't exist in the eyes of the function. Now, Python will try and automatically match things up, but it's not a good practice to do that. And the better practice, if you need to, within a function, refer to a variable, such as a list, in this case, that's outside that function, i.e. it's in the main block of code, it's not in this function block, then you should use the global keyword. So here down out in the main block of code, I've set up this list. I've called it list of queuing times nurse. Now, I can't set that up in the activity generator function. I need to set that up in the main function, in the main block of code, but I do need to refer to it in here. So the first thing I'm going to do in my activity generator is to say, use the keyword global and then refer to this function name. This variable name, which is the name of our list that I set up down here. And what that basically does is it says, okay, I'm going to refer to this thing that I've called list of queuing times nurse. This isn't a new thing that I'm creating in this function. This is something I've set up outside of you in the main block of code. So by using the global keyword, it says, when I say list of queuing times nurse, I mean the thing I set up outside that's got that name. If you weren't to do that, then it would set up a new variable within inside this function called list of queuing times nurse, which is not what you want. So we just use this global keyword to say, this is the function I'm going to be talking. This is the variable I'm talking about. So now within this function, every time I refer to list of queuing times nurse, it's talking about this one down here. So it's talking about this global list. So all I need to do then is, once I've calculated my queuing time with the nurse, by taking away the time they entered from the time they left, I can just say, right, append that time to that list of queuing times nurse. And when you call this, it'll call it on this because it knows you're referring to this list out here. So if I were to run this, sorry, just the other thing to say. So at the end, I've got this all running in the same way. The only thing I've got here, though, is after the simulation's finished running, I just get it to calculate the mean from that list. So calculate the mean list of from the mean list of queuing times, and then get it to print that out. So if I run that now, this time the simulation's run, and it said the mean queuing time for the nurse was 4.04 minutes. So it added all of the queuing times in this particular run. And then at the end of the run, it then took an average over that list. If I were to run that multiple times, you may see quite a bit of variability here. So this time it's nearly 17 minutes, this time it's 8 minutes, this time it's 7 minutes, etc. So that will indicate to you, okay, I definitely need to run this lots and lots of times because there's going to be a good amount of variability in the results depending on what happens in the random sampling. So that's all you need to do to add in your results that you want is set up your places to hold them out here, and then use the global keyword to say in the function, this is what I'm referring to, and then I can just add those results in to that global list. Okay. Right, I've been talking for long enough, so it's time for you to have a practice and have a go at doing this. So what I want you to do is to work in groups. I want you to build a discrete event simulation model in SimPy of this system below. So in this system, we're basically modeling a very simple GP surgery system. So we've got people arriving at the GP surgery, and they're arriving on average every 3 minutes. They're then queuing and waiting to be registered, and we need a receptionist to do that registration. On an average, that takes 2 minutes. They then wait to see a GP, and they need a GP, obviously, to do that. And that will take, on average, 8 minutes for the consultation. And then one of two things will happen to them. They'll either leave the system with no further action, so they'll go into a sync, or a quarter of them will then go back to the receptionist, and they will book a test, because these are the people that need a test booked. So they'll then queue for the receptionist, but this time the receptionist is going to book a test, and that takes on average 4 minutes. So people arriving, they get registered at the we need the receptionist to do that. Then they wait to see a doctor, and they spend an amount of time with the GP, and then 3/4 of them will leave the system, but a quarter of them will then queue to book in a test. So here we've got an example of 2 different activities that are served by the same resource. So the receptionist is doing both these things. They're registering new patients as they come in, but they're also booking tests for a quarter of them. Now in our model, we've got 1 receptionist and 2 GPs. I want you to build that model. I want you to run the model for 8 hours of simulated time. I'd advise you use your time units to represent minutes, because you need to specify your process times and inter-arrival times in minutes. And I also want you to add functionality to the model that will calculate and print the mean queuing times for each of these 3 queues. So the queue for the registration, a queue for the GP consultation, and a queue for the test being booked, along with the mean time in system, i.e. the time from the point at which they arrive here and start queuing for registration to the point of departure. And there are 2 different ways in which they could depart. They can either leave, sorry, I've just realized there should be another arrow down here that says sync as well. They either leave straight after the GP consultation, or they leave after they've booked the test. There's 2 different ways. So you need to capture this being the start time they enter the system, and then depending on what happens to them, either this or this will be the time they leave the system. So you're going to calculate and print those 4 times, the average times, the 3 queues, and their total time in system. And then for extra points, extra brownie points, then I want you to plot a bar chart showing those times. But don't worry if you don't get to that bit. I'm going to give you an hour and insist that you do work in groups for this, because obviously this is your first time building a model. So bounce ideas off each other. I promise I will remember to enable screen sharing for this. Although if you do have any issues, sometimes even if I do it globally, it doesn't allow me to, doesn't allow you to do it. I can come in and fix that for you. Any questions about that? No? Good. Okay. I will put you, let me stop the sharing. Pause the
times. Obviously on the other list, we thought there were some inter-arrival times which we put in first of all and then took out. And then we added the mean registration time, mean GP consultation time, and mean time to test booking. And the other two things we added were the resources, which were a receptionist and a GP, although the receptionist is used twice, once for registration and once for test, but it only needed to be in there once.
Yes.
And then basically we looked at the original models that you went through. So you set up your first patient counter, and then you basically pass it all of the variables that you put in the function at the top, plus a new one for patient ID. And I think that those are the steps that you went through, that you just don't, you just set up those 4 processes.
Yep.
Time. And then you have to then define what activities you're going to want the patient to go through. And again, we passed it the same environments in the function at the top, except the inter-arrival time. And we gave it the patient ID as well. The global bits we put back in afterwards. So we didn't do those to start off with. But so we set off in the system, the patient enters the surgery, and you take the time that they enter the surgery. So the first thing they do is they interact with the receptionist, so to register. And again, this is pretty much exactly as the examples. What we added in afterwards was this list, so that we can then do the mean of all the registration queuing times. So after they finished queuing for the receptionist, they then queued for a GP consultation, and again it's the same setup. So you've got the when they left the queue and started seeing the GP is what this particular line here is about, time left GP cons queue. And then you get to the next bit, which then decides whether or not they're going to go for a test or not. So if they do go for a test, which is 25% of the patients, you then have an interaction on requesting a test booking. And if they are in the 75% that don't go for a test, you don't do anything with it. So I kind of like stuck a comment in here just to say the patient needs a surgery, just to keep in mind that that's what happens to everybody else.
Yeah, that's not a bad idea. And in fact, you could even have the else uncommented, as long as you'd have to put something other than a comment in the else block, but you could use the pass keyword, and that would then allow you to say, if you wanted to add something else into that, you could just reiterate it. But it's a good idea to put that in, so that you're reminded there could be something else that happens. It's just you're not modeling that at the moment.
And then we did a calculation to work out how long the patient has been in the surgery altogether, which is when they left the surgery and from when they first entered the surgery. And then we get to do all the fun bits, which is you set up the environment, you set up the resources that you want. So it's 1 receptionist and 2 GPs. Then you set up all the parameters which were given in the example. So the inter-arrival time, so the time they come into the surgery before they see the receptionist is 3 minutes. They spend 2 minutes with the receptionist, 8 minutes with the GP on average as a consultation, and 4 minutes queuing to book a test again.
No, that's 4 minutes for the test. Was it?
No, I think it's to book the test, wasn't it?
Oh,
Yes.
where's the time?
Oh,
for the
no,
test?
sorry, no, that is
4 minutes for the test.
yes.
Oh, is it?
Yeah.
Okay.
Because we don't know how.
Oh, that's 4 minutes with the reception to book the test. Yeah.
Yes.
Yeah.
Okay. Yes. Because the queuing times are the bit that's random.
The variable. Yeah.
Sorry about that.
That's all right.
So ignore the queues bit, because that was added in afterwards. So then what we did was we started our arrivals generator, and we passed it all of the variables that went into the setting up the patient at the very top. And then we ran the simulation for 180 minutes, and it worked. So it didn't break, which is great. And then we went back in and we added in the queues to hold the list to hold all of the queues. So there were 3 different queues in our system, so registration, GP consultation, and test booking. And when we set those up, we then went back in and stuck the global variables in the patient activity generator function. And when we added those in, you then had to add in the bit which appended it to the list that we'd set up, for one for queuing, one for GP consultations, and one for booking. Where is it? There. And then we ran it again, and we got some results which were here. So when we ran this model, this time, it was 10.8 minutes for registration, 46 minutes for GP consultation, queues to see the GP, and then 10 minutes for test bookings. And then we were starting to get clever and try to do the subplot bit, but we didn't have enough time before we got broken out of the breakout room.
Yeah, no worries. Well, that was fantastic. Well done.
Shall I just run it again?
Yes, do run it. Yeah, let's see it working.
So there we go.
Fantastic. So, I mean,
Results.
what's nice as well, so obviously you're going to get a slightly different result each run. I'll talk a bit more about that in a moment, but you can see just from this that you may have a problem around waiting for the GP, because you're getting very high waiting times to see the GP by the look of it. So that might indicate that's where your problem is in the system. Yeah, fantastic. That's really good work. Really managed to do virtually everything there. And of course, you've created a discrete event simulation of a system, and really that's all there is to it. That's how you build a discrete event simulation. There's some extra little nuances that I'll talk about briefly now, but broadly speaking, that's how you build. That's the core of how you build any discrete event simulation. So I won't run through the solution, because you've basically done that for me, but I will make sure the solution's shared, so you can look back through that, and that'll include the plot stuff as well at the end. It looks like you're pretty much there with that as well.
No, we weren't. This was Terry reading it to us.
Okay. No worries.
Hadn't figured that one out.
Okay, so
sorry, with that bit though, if you wanted to, because it's all very well just having lots of different graphs that show each time you went through it.
Yeah.
How would you collect a whole load of results and then show your average of all your results?
I'll come on to that now. So,
right, sorry, thank you.
That's all right. No. So, yeah, so there's a few extra little things that I want to talk about in terms of how you would build on these models and different features you might want to add in, including having sort of multiple runs and collecting results over lots and lots of runs. The first thing, which I touched on very briefly at the start, was the idea about having multiple generators. So as we said, we may have more than one way for our entities to enter our system in the model. So our patients might arrive at the ED, they might self-present, or they might arrive by ambulance. Now it might be that it doesn't matter for your model, in which case you may want to just capture just a single arrival point, and just your distribution would capture the variability across all ways in which people can arrive. But if it does matter, or if the rate of arrival differs significantly between those ways, so if you've got many more people self-presenting or much more regularly than people turning up by ambulance, for example, then you probably do want to model those entry points separately, so that you can have your own sort of distribution for each. For example, in our GP surgery example, it might be that people coming into the same place and using the same resources, but for different reasons. So if you think back to the first session we did on this, we had a system where people were coming in to see the nurse, and they might be having a test, or they might be seeing the nurse for a weight loss clinic, or for the stop smoking consultation. And we said that you could have 3 different entry points, and we talked that was the model that you designed a conceptual model for in the first session. So there's lots of situations where you may want multiple discrete event generators generating your entities. Regardless, it's really easy to do that in SimPy. We simply just set up more than one generator. So if I open up SimPy 5, have a look at this one. So here we've got exactly the situation that I was talking about from the first session, where we've got people coming in to see the nurse, either for a weight loss clinic or for tests. And so here we've simply just set up 2 separate patient generators. So I've got one patient generator, which is for people coming in for the weight loss clinic, and that'll have its own inter-arrival time. So there's a certain rate associated with the people that are coming in for the weight loss clinic. And then down here, I've just set up another patient generator, and this one's got its own inter-arrival time for people arriving for tests. And in each case, so in this case, they're going through separate processes. So in the weight loss generator, it's creating patients who are going down this route, which is to go for the weight loss stuff. It's using the same resource of the nurse, but there's a slightly different process times associated. Whereas on the patient generator for the tests, people coming in for tests, they get sent off to a different generator, which is describing what happens for the test process. Now, of course, that may not be the case. It might be you just have two generators, but then exactly the same thing happens to them. So it may be that you have the same generator that's called in here, and that's absolutely fine too. But in this case, we've got essentially the same resource, the nurse, but they're doing two separate things, and they've essentially got two queues that they're looking after: people coming in for weight loss and people coming in for tests. And the rate at which they arrive for weight loss clinic and for tests will differ, and the time the nurse spends with the patient will differ depending on if they've come in for a weight loss consultation or for their test. So we can model those things separately. But at the heart, all we've really got to do is add in as many generators as we want. And then the only other change that we make is where we start off our patient generator down below, we just set them both off. So if we've got more than one, we just set all of the patient generators going. And then basically, these things will then just start churning out patients at the rates at which you've specified. So it's really easy to put in multiple entry points into the system. You simply just create another generator and then make sure that you start that generator going down in the setup. So one thing you'll have noticed in doing the model that you've been doing this morning is that every time you run the model, you get quite significantly different results. And that's common in a lot of stochastic models where, remember, this is a stochastic model because it's got randomness in it. We are, each time that we run it, the patients who are coming in on average every 5 minutes or whatever it is, but we're randomly sampling. So we're randomly sampling from a distribution with that mean, but the actual numbers that are used in that particular run will differ. And that can lead to very different results, particularly if the model is at if the system is at tipping point, where it could collapse at any moment. And therefore, if you get, as we saw earlier in the example, with the people queuing for the nurse, and they're spending on average a minute longer with the nurse than they are the rate of arrival, you're expecting to see a queue build, which means they're taking a little bit longer to be seen than the rate at which they're coming in. And therefore, if something goes wrong, if one patient, as we saw, takes much longer, spends a much longer time with the nurse, it can have a really quick knock-on impact where suddenly you've got a massive queue that's built up now. And that obviously will significantly impact your results. Now, that may well be interesting to look at that run on its own, but if we were using this model to generate some results and some insights about our system, what we should do, then we should run this model lots and lots and lots of times to see what overall effects are happening within the system. And the way we do that in SimPy is we basically put all of the setup stuff, so all of the stuff that you wrote around, setting up your parameter values and starting off your generators and all that bit that's outside of your generator function declarations, all of that, including the establishment of the environment, we just put it all into a for loop. And then we basically specify the range as the number of runs we want. So we say, if you want to run it 100 times for X in range 100, do all this. So run that up, set up a new environment, set up these parameter values, run it for this length of time, and then go back through again and do it again and again and again. So we just put it all in a for loop. That also means, however, that the simulation will reset and start anew after each and every run. So if we want to be able to store the individual results from each individual run, which we're going to need if we're going to calculate averages, then we need to do one of two things. We either need to have a global list outside of the loop that will store the results from each run, so at the end of each run, it dumps in that the results from that run so that we can refer to them later and once all the runs have completed. Or we could just write the results of each run to a file. So every time the simulation runs, it'll complete its run. At the end of that run, it will take the averages, so look at the average queuing times, whatever it is that you're looking at, and then it'll write those results to a file. And then each time it runs through, it'll just add to that file. So by the end of all of the runs, we'll have a file that will list all of the results from each of the runs that we've got. So let's look at that in action. So if we look at SimPy 6, here we've just got the same models I just showed you with the 2 generators. So people coming in to see the nurse either for a weight loss consultation or for a test, and the 2 different activity generators, one for people coming in for weight loss, one for people coming in for tests. So here we're going to set up and have it run 100 times. So I've set up, I want the number of simulation runs to be 100. And then what I'm going to do here is to open a file that stores the results of each run, and I'm going to call it nurse results.csv. And the first thing I'm going to do before I start all my runs is I'm just going to write some headers, some column names, so that I know what these results relate to. So I've just opened the file, and you'll be familiar with this from the CSV stuff we talked about. So you can set up a new CSV writer with a delimiter of a comma. And then I just want to write a single row where the first entry says run and the second entry says mean queue for nurse. So basically it's just going to be a CSV file where the first column will be the number of the run and the second column will be the mean queuing time for the nurse in that particular run. So then all of this setup stuff is exactly as you had before. The only difference is that it all goes inside a for loop now. So in this case, I'm going to say do all of this thing, but I want you to do it for run in range number of simulation runs, which I've specified up here as being 100. Now, I could just specify in hard code 100 in here if I wanted to. That would be fine. But it's better practice to keep that separate, so that if I wanted to say, okay, I want to I want to do 500 runs now, I can just look up my parameter value and change it there, and it's much neater to do that. So everything else in here is exactly the same as it was before. It's just that we're now going to do it 100 times. After at the end of each iteration of the for loop, the only extra thing we're going to need to do is to write the results of that run to file. So here I've just set up a list. This has gone through one run of the simulation, run for 2 hours. It's gone through the run. I've calculated the mean queuing time for the nurse. I've just taken the mean of the list of queuing times within that run, as you've just done. I'm going to print that out, but then I'm going to write the results of that run to the file. So here I've set it up as a list because that makes it nice and easy to write. So I'm saying list to write, and the 2 components of my list are the run number, which I've just called run. Remember, we automatically get that from the for loop because I'm just using that as the index, and the mean queuing time for the nurse, which I've calculated up here. So that list is just 2 elements: the number of the run and the mean queuing time for the nurse in that particular run. And then once I've got that, I can just write that list to file. So I open my file in append mode. Remember, we use A to say, open this file, but open it at the end of the file so that what you write goes on the end of that file. Don't overwrite what's already there. So it'll start a new line. We tell it it's delimited by commas, and then we just say write that list. So it'll then write on the next line of the file the run number and the mean queuing time. So once it's done that 100 times, we'll have a CSV file, which I'll show you in a second, which will have 100 entries for mean queuing times for that. Now, what we might then want to do is then we could, after our for loop, so after the 100 runs has taken place, we could then read those results back in, and then we could calculate the mean, etc. So here I could say, right now you've written all those results to the file. I'm going to read that back in. Now, you may have seen this. I don't think I've shown you. I don't know if Mike's shown you yet. There's a very handy little shortcut for reading CSV files straight into a Pandas data frame. And it's a really nice little feature of Pandas that allows you to do this very easily. So if I read this straight into a Pandas data frame, rather than going through and reading it line by line and doing all that stuff you've done before, you can literally just say, set up a data frame ready to store this. And I'm just going to say PD, which is our alias for Pandas, which I've imported at the top. I'm going to say pd.readCSV, and then I just tell it the CSV file. And Pandas will then automatically weave its magic. It'll read in that CSV file, and it'll automatically store it in a Pandas data frame. And because I've given it in my file, I gave it these little column headers that I wrote at the start, it'll automatically set up the Pandas data frame with the column names exactly as I've got them. So run and mean Q nurse. And literally that one line of code will do all of that for you. It's such a lovely feature of Pandas that allows you just to read in a CSV and dump it straight into a Pandas data frame so you can work with it really easily. So once you've read that in, then let's say I want to take the average queuing time for the nurse across all of the runs. So I could then say, take the mean. Remember, in Pandas, we could just refer to the column that we want. So in this case, mean Q for the nurse, and just call the mean method on that. And that'll give me the mean for the queuing time. Might also be we want to look at the maximum and the minimum queuing times as well. So I could, again, being a Pandas data frame, I can just call the .max or the .min methods on that particular column. So it allows us to really easily then get some results. So let me just run that so you can see how this works. So if I run that, so this has now run that model 100 times. So these are the individual results that I'm printing out from each run. Now, if I go into the file, where are we? It'll be in here. You can see it's created a file called nurseresults.csv. If I open that up, I'll open it in a spreadsheet so you can see how it looks. And you can see that's what it's done. So it's gone through, and for each run number, it's put the run number and then the mean queuing time for the nurse for that particular run. And you can see there are some runs where we had presumably a run of good luck where there was actually a very low queuing time. That's a combination likely of people not spending very long with the nurse and or people arriving quite far apart. And you may have days like that, but then you may also have days where the mean queuing time is much higher. So if we look up here, the one just before that, run 21, the mean queuing time was nearly an hour. So there's quite a significant difference there. But we can, by running it lots and lots of times, we can get a general feel for how the system is running. And because I've got in my code that I read that back in, I can then calculate the mean Q over the whole trial. So if I do that, you can see if I run it over 100 runs and then take the average over that, the mean queuing time is about 24 minutes. The maximum is about 62 minutes and the minimum just under half a minute. And if I were to run that again, you'll see there's much less variability in that overall mean. So 22 minutes for the trial, 22 minutes, 24 minutes. We're getting much less variability because we're looking at the trial as a whole. This batch of runs, we're taking into account that there'll be some good days and some bad days, but we're looking at the general behavior of the system and getting those average results in that way. So that gives us a better sense of what the actual queuing time for, in this case, for the nurse, would be within the system. And the number of runs you select to do, you can either, sort of just do so many that you're pretty confident, or you can try and work out where more statistically where you're how many runs you need in order to get a good level of stability in your results. So that's how you would do multiple runs, and it's fundamentally important to do multiple runs whenever you're doing any discrete event. Well, most modeling types actually, but particularly for discrete event simulation, you do want to run things more than once. My advice would be to stuff everything in a for loop ready for that, but just when you're initially building up your model, just have it run once So you just have a number of runs as one. And then once you're happy everything's working, then you can start running through it lots and lots of times. Another key thing you need to consider when you're doing a discrete event simulation is something known as warm-up. Now, a potential problem in the models we've looked at so far, and in many discrete event models, is that by default, we're assuming that when we start our model, it's empty. There's nothing in it. So when you built your model a minute ago, your GP surgery had no patients in it. So the first patient comes along and they're immediately seen because nobody's waiting. Now, in some cases, that might be fine. So if you're simulating, for example, a day of minor injury unit activity where patients turn up in the morning and then everybody's kind of seen and then nobody's left, hopefully inside when it closes, then that's okay. If you're just modeling a day in the life of a minor injury unit, that would be fine. It starts off empty, then you churn through everybody and then it closes. But think about if you're modeling something like an emergency department or a hospital more generally. Those kinds of systems are never empty. You never have a completely empty ED or an empty hospital. And so if we're going to model this, but we start our model where everything is empty, then our results are going to be skewed by the fact that initially there was no waiting time because people were turning up to the ED and, oh, great, everybody's free. All the doctors are sat around waiting. This is fantastic. They're flying through the system. Now, sure enough, the queues will likely start building. But because you're collecting those results at the start, which are not representative of your real world ED, that your results are going to be skewed. It's going to underestimate the actual level of delay in your system. Fortunately, there's a really simple solution that you can use whenever you're building a discrete event simulation, and that is you can use what's known as a warm-up period. And basically, a warm-up period, you run the model as normal, so you start off as empty, and you start the model running, but for the duration of whatever warm-up period you specified, it doesn't collect any results. So it goes through the motions and it has people coming in and being triaged and whatever it is your model is doing, and it goes through and starts filling up, but none of these results are being collected because it's acknowledging that it's allowing the model to warm up first. And what we then do is after the warm-up period, that's when we start collecting results. So once the system has got into a state where it's more representative of the kind of levels that we would see, then we can start collecting results after that. Now, the length of that warm-up period is going to vary depending on what it is that you're modeling. It might be that you just choose a really long warm-up period where well, if I just run it for 2 weeks of simulated time, by that point the system will be sufficiently full, and that's okay. So you could do it that way, or you could run the simulation multiple times and you could track the results over time to see when a steadier state appears to be reached. So when are you getting to that place where things seem to be stabilizing and you seem to be getting that level of fullness that you need. But either way, however you want to judge what that warm-up period should be, it's really easy to add a warm-up period to SimPy models. And all we do is we basically just use some conditional logic, so some if statements, to make sure that results are only collected if we're not already in, if we're still in that warm-up period, the results won't be collected. And only if we've passed that warm-up period will we actually collect some results. So if I dial up SimPy 7 here, so here we've got exactly the same model again. We've got patients coming in to see the nurse either for weight loss or for tests. Exactly the same way as we did before. The only difference is that this time I've set up both a warm-up period and a results collection period. And I've separated those things out just so that it's explicit what we're doing. So basically what this says is I want the model to run for 2 hours, 120 minutes. But during that time, I don't want to collect any results. I don't want that to contribute to my average results that I'm looking at. But then after that time, I want to collect the results for a further 2 hours. And I do want the results collected during that simulation time. So the simulation is going to run for 4 hours in total, but it will only collect results from the last 2 hours. Okay. So what I can do just to make sure that happens is I can, whenever I go to add my results, so if you remember back in the activity generators, this is where we're adding our results. So you can go to one where it's collecting it. So here, I've got the calculated the time that the patient was in the queue for a nurse test, and I've calculated that as the time they left the queue minus the time they entered the queue. All good so far. Now, the next thing we'd normally do is then to add that to our list of queuing times. But all I've done is just added a little if statement here to check to make sure we're not still in the warm-up period before I do that. And because SimPy, the SimPy environment allows us to access this environment.now, which basically says what's the current simulation time, I can check that really easily. I just say if environment.now is greater than the warm-up period. So in other words, have I passed 120 on the simulation time? If I have, then I can add the results. But if not, this won't be done. So the simulation will still run, it will still model these patients, but that result will not be added. So it will just carry on and it'll go through the motions, but these results won't be counted. And that's all you need to do. So you just sorry.
Can I just ask one thing? I'm sorry to interrupt again. In a similar way to what you're doing there, in the D department, the demand, of course, changes as variable during the day.
Mm-hmm.
Sometimes it's very busy, other times it's very quiet.
Yep.
Could we use the same process within the patient generator to change the interval to make it more busy at certain times of the day?
Yes, exactly that. And you would very often do that. And what you would likely do would be to change your mean that you're sampling from. Essentially,
Yes.
essentially you sample from a different distribution between midnight and 8 a.m. maybe from 8 a.m. to 3 o'clock or whatever it may be.
Yes.
So you can constantly then take a simulation check to see what time it is, and then the correct distribution will be sampled from. So yeah, absolutely, you would very much do that, and that applies for a lot of healthcare modelling, particularly for things like EDs, where the level of incoming activity is going to vary significantly over the course of 24 hours. And indeed, of course, you can take that further. You can also, if you're modelling, beyond a day, you may want to have different days of the week that have different levels of incoming activity as well. So yeah, absolutely, use exactly the same principle, that you're checking the simulation time and then doing something different depending on what the time is now.
Okay, thank you.
So that's all we need to do to add our warm-up period, or as we just said, to do different things depending on what the time of day is. So the last thing I just wanted to mention before we close, and I will also, there was an exercise I was going to get you to do, which I will briefly go over, but obviously you're not going to be able to do it in 3 minutes unless you're really going to impress me. I'd have a go at it in your own time, just to give you a bit more practice on SimPy, and I'll go over that in a second. But the last thing I just wanted to mention, because it came up earlier as well, is something called containers. So far, we've looked at resources in SimPy as being these discrete identifiable entities. So we've got 3 nurses, we've got 2 receptionists, we've got 5 doctors, whatever it may be. They are discrete and continuous, and I need a doctor here, I need a nurse, whatever it might be. But what if what we actually wanted to model was something more continuous? In other words, to model some sort of homogeneous mass of resource, some sort of pool of resource. So the common example that's used in SimPy is, imagine you were fueling your car, and the fuel level essentially, or your resource, sorry, is petrol. And so you're gradually taking things out of your petrol pumps, depleting the resource, and then you're having fuel tanks come along and refill it, etc. So it's still a resource, but it's a continuous mass of resource. You've got users who are taking out amounts. And to think about things, and this is the example that somebody mentioned earlier, so you might want to think about, rather than individual nurses, you may want to think about simultaneous nurse time in use. So you're thinking about time of resource, and from which you may want to take from the available time or add back to that pool of time as your incoming activity fluctuates. And you can do that in SimPy really easily using containers rather than the resource class. So if I show you an example, So let's look at SimPy 8. So here I've just got a very simple model where I've got patients who are coming in and they're being generated here in the patient generator. And then in the activity generator, then we're basically, they're seeing a district nurse. But we're modeling that not as a district nurse coming to see them, we're modeling it as an amount of time that is taken out of the district nursing pool. So here, rather than, so if I scroll down to the bottom first. So before, when you set up resources, we set up an instance of the resource class, and we said it had a capacity of whatever it may be. Here, I'm setting up essentially district nurse hours or district nurse minutes. And I set that up, rather than SimPy.resource, I set it up as a SimPy.container. And there's three things I specify here. So I give it the environment, as I would for a resource. And then I also specify an initial value. So what value will it start at the start of the model? And then a total capacity. So how full can this thing get? Now, in a lot of cases, for the sort of models you'll be doing, if you are using containers, you'll likely want to keep those things the same, or certainly not have the initial capacity go over the total capacity, because essentially what I'm doing here, I want to check to make sure that I'm not putting back more hours than I had available at the start. Because if I have, then something's gone very wrong. It might be you are modeling something where you've already got some district nurses who are currently active, and then you could have more hours being put back because you're sort of modeling something where you're halfway through certain processes. I wouldn't tend to advise doing that, but in that instance, you may have a higher capacity than the number of hours that are available at the start. But generally speaking, you probably want to leave those the same. So this is basically saying, I've got district nurse minutes, I've got 1,000, I can't remember if it's hours or minutes, doesn't matter, 1,000 minutes of district nurse time, and I can have a maximum of 1,000 minutes of district nurse time. And so all we need to do, whenever we need to use some district nurse time, then we do exactly the same as we've done before. So I've got my global keywords to store the queuing times. I've recorded the time at the end of the queue. And here, what I'm now going to do, rather than request the resource, so here's where we'd normally say with district nurse.request as REQ. Here we do it slightly differently. So what we do is say, okay, how many hours, minutes of district nurse time am I going to need? So we're going to randomly sample that here from an exponential distribution. So, and I've passed in a mean to be the mean visit time. So let's say the mean visit, well, what is the mean visit time? It is 60 minutes. On average, it's an hour. So it's going to sample from an exponential distribution where the mean is 1 hour. That will then represent the number of district nurse minutes that this patient will take up. And so then what we do, as I've just printed out a message saying we've got so many district nurse minutes available before any were requested. Then if I'm using a container, what I do is I use the get method on that resource. So I say, basically, grab me this many minutes from that container, this many units of stuff. So here I say district nurse.get, and then however many minutes I've sampled up here. So if I've sampled 70 minutes, then 70 minutes will be taken from the container. Now, it's very important when you're doing this, because you're not using a with statement in the structure, you need to make sure you're using the yield keyword to say freeze in place until you've got 70 minutes that you can give me. Because if you've only got 20 minutes left in the pot, then what you actually want it to do is to wait. You need a queue to form here. What you don't want, if you were to remove that yield keyword, it would just carry on as though it did have enough minutes, and you don't want that. You want it to, if you haven't got enough minutes available, you want it to wait. So we grab the number of minutes that the number of units of stuff, in this case minutes, from our container using the get method. Then I just print out a little message saying now we've got this much left in our district nurse container. We do all our standard thing around queuing, calculating the queuing times, etc. here. I'm going to call the timeout as I did before, because I want this function to freeze for that amount of time. And remember, before we were freezing with the resource alongside us. We're doing the same thing here because we're freezing. We've taken out however many minutes from our container, and now we're freezing. So those minutes are still removed from that container. When control is passed back, when that amount of time has has elapsed, we then continue from this point, and then we put, in this case, we're going to put back those minutes because we're putting back that amount of time. Now, it may be that for your particular model, you're not dealing in time, and it might be that you've got another type of container, in which case you would your timeout may not represent the amount of stuff you've taken from the container. But in this case, we're using it to model time, and so we're saying basically, I've sampled 70 minutes. I need to spend 70 minutes with this nurse. So grab 70 minutes from the district nurse container, and then freeze this function for 70 minutes of simulated time. And then when you come back, you can put those 70 minutes back, and you've got that nurse time back. So it runs in exactly the same way as before. It's just you're dealing with getting and putting, so getting from and putting back to a container. So if I run that, you can see the model runs through, and it has varying levels of district nurse minutes available both before and after the request has been made, and then I can look at my average results over the trial. So it's a different way of thinking about resource, and sometimes that will make more sense, particularly in community settings. You may want to think more in terms of district nurse time or resource time rather than individual nurses or other resource. Okay, so the last thing I just want to cover, because it's lunchtime, I'm just going to talk you through the exercise to have a go at in your own time. Do have a go if you get a chance, because it's good practice for your model building skills. So what I want you to do is to extend the model you built in exercise 1 to capture these extra things. So I want you to capture the fact that calls are coming into reception on average every 10 minutes, and which lasts an average of 4 minutes. And these are answered by the receptionist. And this is the same receptionist that's also registering patients who are arriving at the surgery and also booking in tests for a quarter of your patients. Don't worry about adding any results for the call queues or adding those to the system timing system results, but you can if you would like. But essentially what we're doing here is just modeling a drain on the receptionist time. So it may be, and you'll have situations like this where you're modeling something where you're not particularly interested in the queue for the phone. You're interested in this over here, but you're modeling this because you need to capture the fact that the receptionist is also being called away to answer these telephone calls. So you're capturing the drain on the time and what impact it has on your bit of the system that you're interested in. I also want you to include a warm-up period of 3 hours before 8 hours of results are collected, and also add functionality to run the simulation multiple times. So have the simulation run 100 times and then take the average results over those runs. So I will share the solution to that as well with you. So, but have a go at that in your own time on your own first, and see if you can build up that first version of the model to incorporate this extra stuff, and then have a look at the solution to see how I've done it. Any questions before we break?
11-hour days, you're a hard taskmaster.
Sorry,
Yes.
I do have another question.
Okay.
That is that we've now got these resources in containers, mm-hmm. which is sort of more realistic. But on top of that, they also have one thing is they would have breaks. Mm-hmm. How you would factor a break in, and number 2 would be that while there are so many minutes, you'd have to have a discrete person, if you see what I mean, not just a part of 2 people.
Yeah, I suppose, I mean, it depends. So you'd need to think about the best way to model all aspects of your system. So maybe you have a mix of things. It may be that you have some discrete resources as well as containers
Yes.
for different aspects, and that's okay. You can deal with both at the same time.
Okay.
If you're dealing with breaks and things, you could factor that in. It depends how you want to model that. So again, that comes back to the level of detail. So you may want to explicitly model those breaks happening at, every so many hours, or it might be that you just take that into consideration in terms of your overall day or whatever you're modeling, and there's different ways of doing that. But yes, you could do all of those things.
So could you have those breaks as sort of other processes that take that person's time up?
Yes, you could. You could model that as a break process where it's basically requesting that resource, and that resource is then held for a certain amount of time.
Okay, that's great. Okay, thank you very much.
Yeah, no worries.
Thanks.
Okay, great. I hope that's been useful for you this morning. I hope it's given you a glimpse into how you build these discrete event models, and hopefully you've seen that it actually, once you get the hang of it, it's actually quite straightforward to build these things and to build some really powerful discrete event simulation models. So in the session next week, if you're coming along to that, we look at a bit more at SimPy, and basically I'll show you how to do all this using an object-oriented framework, because you've probably already noticed that passing around your environment and your resources and your numbers between functions is a bit of a pain, and it can get quite messy quite quickly, even with these relatively simple systems that you're modeling. So using the object-oriented approach, you can create more elegant ways of doing this.
Are you okay if we sort of try and do one ourselves with our own sort of processes at work?
Yeah, absolutely. Please do. I think that's a fantastic way to practice using these skills. Absolutely.
Okay, great.
Great. Okay, fantastic. So Mike, I think you're doing this afternoon session on GeoPandas, and is it, I think we start with the Zoom call at 1:30. Is that right? I'm guessing Mike isn't here. I'll play Mike. Yes, that's right, Dan. You've got it right again. 1:30 it is.
Mike's on mute.
Mike was
mute?
talking, but nothing was coming out.
Oh, right. It's like all my dreams come true. Are you there, Mike? No, we still can't hear you for some reason. Okay, it's 1:30. Have a look on Slack. Look at the Module 6 channel, and you'll see the instructions, what you need to do. Most of the afternoon, you're going to be working on a pre-recorded video, but there'll be a live session at the start and the end. And don't forget, obviously, tomorrow, you must submit your project pitches by the end of tomorrow, so do make sure they're posted. And don't forget the test on Thursday. And also don't forget, if you're coming along, we've got 2 more training sessions tomorrow, looking at the advanced network analysis and something else. I think it's Mike again, machine learning, I think. So if you're coming along to either of those sessions, make sure that you are following the instructions on Slack for those.
Yeah, just to say, sorry, I blame my wife. She stole my microphone earlier. 1:30 for the Zoom call. It's in the Slack channel on geographic modelling. So we'll kick off there.
Brilliant. Thanks, Mike.
Could I just ask somebody when everybody goes just a quick word about my project?
Yeah, sure.
Okay, so I've having spoken to you last week, and you said it needs to be something that's actually going to have results.